Hi everyone, so my name is Zoey and I'm gonna introduce the theorem 316 to definition 319. First, the theorem 316. Let L be a line in a hyperbolic plane. Array K is a limiting parallel to L if and only if every subarray and every superarray of K is a limiting parallel to L. There is a if and only if in the theorem, so we have to prove this one in two directions. First direction, let L be a line in a hyperbolic plane, and Ts is the limiting parallel to L. According to the lemma 315, the subarray of a limiting parallel ray to L is also limiting parallel ray to L, so the subarray of Ts is also limiting parallel to L. Next, the superarray. So let Ps be the superarray of Ts, and Q is the foot of the perpendicular. So we can form a PV between Ps and PQ if we can show that PV is intersect with line L, and we can say that the PS is limiting parallel to L. So connect the Q and T. This gives us the triangle QPT. QTS is the exterior angle, so it must be larger than the QPT, and the PV is lying between PS and PQ, so QPT is larger than the VPT, the small angle. Next, across to the proposition I-23, we can form a concurrent copy of the VPT, this small angle, with the vertex T and the leg TS. Because TS is a limiting parallel to line L, so it must intersect with the line L. And these two angles are equal. So consider the QTX, these large triangles. So since PV is like crossing the one side the QT and not meet any vertex, according to the axiom of Passig, it must intersect with Tx or Qx. However, Tx is parallel to PV, so PV must intersect with Qx and also the line L, and this is what we want. So PS is the limiting parallel to the line L. So this proves this direction. For the inverse direction, it's quite simple. So first one, suppose every superarray of K is a limiting parallel to L, then K becomes the subarray. So according to the lemma 350, the subarray of limiting parallel ray to L is also limiting parallel ray to L. Consider the superarray. So if every subarray of K is limiting parallel, then K is the superarray of these subarrays. Actually, we proved this one in the previous direction. So the superarray of a limiting parallel to L is also limiting parallel to L. So it's quite simple for this one. And we got this direction, and we proved this theorem. Next, the lemma 317. Let PS be a limiting parallel ray to a line L in a hyperbolic plane. Let Q be the foot of the perpendicular from P to L, and there is then a subarray of L, the WX, and on the same side of PQ, a subarray of PS, the UT, so that the angle XWU is concurrent to the angle TUW. So first, this is the basic graph, and Q is the perpendicular foot. Let's consider to bisect the angle QPS, this one. So since the PD that is formed this angle, the QPD, is less than the angle of parallelism, so PD must intersect with line L. Next, we want to bisect the angle PQD, the right angle. According to the crossbar, so the bisector is passed through the vertex Q, and it must also must pass the side opposite the vertex, is the PD. So it means the bisector must intersect with PD at the intersection R. So next, we drop three perpendiculars from R to PS, PQ, and DQ, and call this field the UVW. There are two situations. So first one, URW, these 3 points are collinear, and the graph will become like this one. And then we get that these two triangles and these two angles are all right angles, and we get that what we want, these two angles are concurrent. However, if these 3 points are not collinear, we have to consider the congruent triangles. According to the angle side, we first consider these two small triangles. So RQ equals RQ, RQW, RQV is the bisector, the bisection angles, and the RWQ or VQ is the right angles. So these two triangles are congruent, and we get the RV equals RW. So similar for these two triangles, we get the RV equals RU. So overall, we get the RU equals RW. Next, connect U and W. Because RU equals RW, so this triangle is an isosceles triangle, and RUW is equals to RWU, these two small angles. Next, take T on PS and X on QW, these 2 points, and this gives us the angle we want, the TUW and the XWU. However, these two angles, the TUW is the complete supplement of the RUW, and the XWU is the supplement of the RWU, and these two angles are equal, so TUW and XW must be equal, and this helps us prove this lemma. Next, the theorem 318. PS is a limiting parallel to a line L in a hyperbolic plane, if and only if L has a subray QT that is a limiting parallel to PS. Also, there is if and only if in this theorem, so we have to prove in two directions. So according to the lemma 317, we can take Q and T on L, and T and S on the same side of PQ, so these two large angles, the SPQ is equals to TQP. And we can draw a QU that is between QT and PQ. If we can show QU must intersect with PS, then we can say that QT is limiting parallel ray to PS. Next, we form a concurrent copy of the angle UQT, this small one, and starting from the vertex P, using PS as a leg, and these two angles are equal. Because PS is the limiting parallel ray, so there is an intersection point with PX and QT is just the point T. So consider the large triangle TQP, this large one. According to the crossbar, QU is passing through the vertex Q, and it must also pass through the side opposite the vertex, is the PT. So there is an intersection point, name it R. According to the proposition I6, consider the triangle RPQ, this one. So these two large yellow angles are equal, and these two green angles are also equal. So this is the left angles, this one and this one, the RPQ and RQP are also equal. So PRQ is an isosceles triangles, and we get PR equals QR. According to the vertical angle theorems, so we get the PRU equals QRT, these two blue angles. So according to the angle side angle, these two green angles equal, blue angles equal, and PR equals QR. So we have the QRT, this triangle, is concurrent with the PRY, which means there has some point Y that is on PS and QU, which also means that the QU must intersect with PS, and we can say that the QT is a limiting parallel to PS. So we get this direction. So for the inverse direction, it's quite simple actually. So this is the graph for the previous direction, and this is for the new one. We want to prove that L has a subray QT that is a limiting parallel to PS, and then PS is a limiting parallel to a line L. So previous one, we have to prove that QT is a limiting parallel to PS, and now we have to prove PS is a limiting parallel to QT. It's just like exchange their position. So I'm gonna go through this one quite quickly. So first we pick the point PS and TS on same side, and these two angles are equal. And we want to prove PU must intersect with QT. Form the concurrent angles, these two green angles are equal, and QX intersect with PS at intersection point S. So consider the triangle QPS, this large one. According to the crossbar, PU must intersect with QS at the intersection point R, and consider the triangle RQP. We have RQP equals the angle RQP equals the angle RPQ. So QR equals PR. And according to the vertical angle theorems, these two blue angles are equal, and we have that there's two concurrent triangles because of the angle side angle. There's two green angles and there's two blue angles, and the QR equals PR. So there has some point Y that QT must intersect with PU, and we get that the PS is the limiting parallel to QT. Yep, we also get this direction, so we finished prove these theorems. And the last one is the definition 319. Let L and M be lines in a hyperbolic plane such that L has a subray QT that is limiting parallel to M. QT is limiting parallel to M, so M and L, these two lines, are limiting parallel lines. So that's all. Thanks.